Okay, we are at section 2.7, analysis model. Now, we've had analysis model in the past, but now we're doing it, that was for constant velocity, now we're doing it constant acceleration. Let's go to the next slide. If the acceleration of a particle varies in time, with the motion can be complex and difficult to analyze. A simple type of one-dimensional motion is where the acceleration is constant. Average acceleration over any time interval numerically equals to instantaneous acceleration at any instance within the interval. Velocity changes at the same rate throughout the motion. The analysis model is the particle under constant acceleration. Replace AX average by AX and take T initial equals 0 and T final to be any later time T to get the acceleration. So acceleration is Vx final minus Vx initial divided by the T by T, the T interval. You can rewrite that, whoa, too many times. Vx final, we're just solving for Vx final. Vx final is equal to Vx initial plus acceleration in the x direction times T for constant acceleration. We can determine the object's velocity at any time t if we know the object's initial velocity, vxi, and its constant acceleration, ax. Figure B, A is the position, figure B is the velocity versus time graph for constant acceleration motion. The graph is a straight line. The slope equals the acceleration. The constant slope is consistent with AX equal to dV dt being constant. Note the slope of the slope is positive, it's positive acceleration. If the acceleration is negative, then the slope will be negative. When acceleration is constant, the graph of the acceleration versus time graph will have a straight line with slope equals 0. So once again, if you look at the figure, we have a position versus time. The B, velocity, is the first derivative of the position versus time graph, and the acceleration is the first derivative of the velocity versus time graph. It's also the second derivative of the position versus time graph. Okay, now I lost my place. Okay. Velocity at constant acceleration varies linearly with time. Average velocity in any time interval is the arithmetic mean of the initial velocity vxi and final velocity vxf. So you have two values, and what is the average between them? You add the two values and you divide by 2. So this is Vxi plus Vxf, V initial plus V final divided by 2. That's the average velocity. Very simple. This only applies to constant acceleration. Okay, very important. Only applies to constant acceleration. Use the equation to obtain position of an object as a function of time. Let's write delta, given that Vx is equal to delta x over delta t, and given that Vx average is equal to Vx initial plus Vx final, let's do some manipulation here. Delta x equals Vx final x final minus x initial. Delta t equals t final minus t initial. If we take t initial to equal to 0, it just becomes t. We can substitute and rearrange x initial minus x final equals Vx average times t. Well, what is Vx average? It's Vx initial plus Vx final divided by 2. We just saw, you can see that up above. So if we solve for x final equals xi plus 1/2 Vx I plus Vxf times t. That 1/2 Vxi plus Vxf is just the average velocity. So to get the final position, you take the initial position times the average velocity times time, and you get the final position. Okay. Now let's look at the. We just got this Vx final is equal to x initial plus the average velocity times t. If we substitute to find the new equation, x final, x initial plus 1/2 Vxi plus Vxi plus at times t. We have the equation, final position of a particle at time t in terms of initial position, initial velocity, and constant acceleration. We get x final equals xi plus Vxi t plus 1/2 at ax times t squared for constant acceleration. So the position versus time graph for motion at constant acceleration obtained in this equation. Note that the curve is a parabola because of the t squared. The slope of the tangent line to this curve at t equals 0 equals the initial velocity, Vxi, and the slope of the tangent line at any later time equals the velocity Vxf at time at that time. Okay? It might seem overwhelming, but you'll get used to all of these equations. Okay. Vxf equals Vxi plus axt. Let's solve for t equals x final minus x initial over a. If we substitute into xf equals xi plus 1/2 t, we get x final equals x initial plus 1/2 we'll get the v times v final minus v initial over a. X sub I equals we have the, remember, if you have a plus b times a minus b, you get a squared minus b squared, and that's what they're using here. And we're going to get Vxf squared equals Vxi squared plus 2ax times delta x for constant a. This is, now notice that this equation doesn't have a time. There's no time in here. So that sometimes this is this can be a very useful equation. This equation gives the final velocity in terms of initial velocity, the constant acceleration and position of a particle. No t involved. And we are going, let's see, we are going to slide 70. Oh, we still have a ways to go. Okay, now for motion at zero acceleration, Vxf equals Vx final equals Vx initial equals just Vx. And x final is equal to x initial plus Vx t when the acceleration equals 0. The velocity is constant, and the position changes linearly with time. Particle under constant acceleration model reduces to a particle under constant velocity model when the acceleration is equal to 0. And this gives us our kinematic equations. It's used to solve any problem involving particle under constant acceleration in one dimension. You have the choice of which equation you use, depends on what you know. Sometimes it's necessary to use more than one equation to solve for two unknowns. Quantities that vary during the motion are position, velocity, and time. Remember, the acceleration is constant. Equations of kinematics cannot be used in situations where accelerations vary with time. So we have Vx final equals Vx initial plus acceleration times time. The Vx average is just the V initial plus V final over 2. X final equals X initial plus 1/2 Vx initial plus Vx final t. That's the Vx initial plus Vx final divided by 2. That's just the average velocity. And then X final, the final position equals the initial position plus the velocity times time plus 1/2 acceleration times time squared. And then the last one is Vx final squared equals Vx initial squared plus 2a delta x, or x final minus x initial. These are the kinematic equations. You're going to want to either write these down or just print this slide and have this slide available to you, because you're going to be using it quite often. Time for a quick quiz. In the figure, match each Vx velocity versus time graph on top with the acceleration versus time graph on the bottom that best describes the motion. It's pretty easy to see that C is equal to F, and it's also easy to see that the A goes with E. It's a constant acceleration, means a constant velocity, constantly increasing velocity. And the increase in acceleration means that the velocity is increasing more rapidly. So D goes to B. Let's see if we got that right. Yeah. A goes to E, B goes to D, and C goes to F. Okay. Imagine a moving object that can be modeled as a particle. If it begins from position x initial and initial velocity vxi and moves in a straight line with a constant acceleration a, its subsequent position and velocity are described as the kinematic equations. Okay, examples are a car accelerated at a constant rate along a straight freeway, a dropped object in the absence of air resistance, an object in which a constant net force acts, and a charged particle in a uniform electric field. Let's look at some examples. A jet lands on an aircraft carrier at a speed of 140 miles an hour with 63 meters per second. What is the acceleration assumed constant if it stops in 2 seconds due to an arresting cable that snags the jet and brings it to a stop? Okay. Because the acceleration of the jet is assumed constant, we can model it as a particle under constant acceleration. This equation, oops, oh, okay, the equation's already there. Oh, that's right, I had to rewrite it. This equation is the only equation in the particle under constant acceleration model that does not involve position. So we use it to find the acceleration of the jet modeled as a particle. And we find out that the acceleration is equal to minus 32 meters per second squared. Okay, if the jet touches down at position x equals 0, what is its final position? Use this equation to solve for the final position. X final is x initial plus 1/2, the average velocity times t. Given the size of the aircraft carrier, a length of 63 meters seems reasonable for stopping the jet. The idea of using arresting cables to slow down landing aircraft and enable them to land safely on ships originated about the time of World War I. The cables are still a vital part of the operation of modern aircraft carriers. Okay, suppose the jet lands on the deck of the aircraft carrier with a speed faster than 63 meters per second, but has the same acceleration due to the cable as calculated in part A. How will that change the answer to part B? Okay, if the jet is traveling faster at the beginning, it will stop further away from its starting point. So the answer to part B should be larger. The position coordinate x sub final will be larger. Mathematically, we see that if Vxi is larger, then x sub final will be larger. Or to the increase, even though it's divided by 2, x final increases, x sub f has to increase. Okay, another example. You are driving at a constant speed of 45 meters per second when you pass a trooper on a motorcycle hidden behind a billboard. 1 second after you pass, after your car passes the billboard, the trooper sets out from the billboard to catch you, accelerating at the constant rate of 3 meters per second squared. How long does it take a trooper to overtake your car? Okay, this example represents a class of problems called context-rich problems, ones where it's the physics of real life. Are you going to get caught by the motorcycle cop? Most likely you are. A pictorial representation helps clarify the sequence of events. Your car is modeled as a particle under constant velocity, and the trooper is modeled as a particle under constant acceleration. Most likely, if you spot yourself being followed by police, you're going to slow down. But in this problem, you have constant velocity. First, we write expressions for the position of each vehicle as a function of time. It is convenient to choose the position of the billboard as the origin and to set TB as the time the trooper begins moving. At that instant, the car has already traveled a distance of 45 meters. Remember, 1 second, it says 1 second after your car passes the billboard, the trooper sets out. So if you make that T0, then you've already gone 45 meters. Okay, the initial position of your car is 45 meters once the policeman starts. Now, using the particle under constant velocity model, apply the equation shown to give your car's position at any time. X of the car is equal to xb plus vx of the car times t. A quick shows that the t equals 0. This expression gives your car's correct initial position when the trooper begins to move 45 meters. The trooper starts from rest at TB equals 0 and accelerates at AX 3 meters per second squared away from the origin. Use this equation to give her position at any time. So you use the x final equals x initial plus vxi t plus 1/2 acceleration times time squared. The trooper, her initial position is 0. Her initial velocity is 0. So all she has is the acceleration, 1/2 at squared. Set the positions of your car and the trooper equal to represent the trooper overtaking your car at position C. X trooper equals x of the car. So your 1/2 AX, the trooper is 1/2 AX t squared equals your XB plus VX car times T. And let's see. Okay, there we go. Rearrange to give a quadratic equation. Solve the quadratic equation for the time. So 1/2 AX t squared minus VX car times T minus XB equals 0. That's our quadratic equation. We solve the quadratic equation using the quadratic equation formula, which is minus b plus or minus b squared plus 2ac divided by 1/2 or 2a, I believe. I don't even remember the quadratic equation. But you do the substitution, you come up with this. Vx car divided by ax plus or minus this radical. Okay, evaluate the solution choosing the positive root because that is the only choice consistent with time greater than 0. Why didn't we choose T? Okay, let's get the answer is 31 seconds. It takes you 31 seconds to overtake you if you do all the substitution. Why didn't we choose T equals 0 at the time at which your car passes the trooper? If we did so, we would not be able to use the particle under constant acceleration model for the trooper because her acceleration would be 0 for the first second and then 3 meters per second for the remaining time. By defining the time t equals 0 as when the trooper begins moving, we can use the particle under constant acceleration model for her movement for all positive times. And that's why we chose uh, t equals 0 as her starting. Okay. Um, what if the trooper had a more powerful motorcycle with a larger acceleration? How would they change how would that change the time which the trooper catches your car? Well, if the motorcycle has a larger acceleration, the trooper should catch up to your car sooner. So the answer for the time would be less than 31 seconds. T is less than 31 seconds because all terms on the right side of the equation have the equation AX in the denominator. We see symbolically that increasing the acceleration will decrease the time at which the trooper catches your car. This ends our discussion of section 2.7. In the next section, we will discuss freely falling objects.